Welcome to The Explainer. All right, let's just dive right in. Today, we're tearing down the Hollywood special effects and getting into the hard physics behind directed energy weapons. We're going to see why making a real-life ray gun is one of the biggest engineering puzzles out there.
Seems like a weird question, doesn't it? A super advanced weapon on one hand and a chunk of frozen water on the other. But believe it or not, the answer gets right to the heart of how you actually destroy something. It all comes down to the absolutely staggering amount of energy you need to cause real physical damage. And to really get our heads around that energy, we're going to start simple with a 50-gram ice cube, about the size of one you'd pop in a drink. If we want to completely annihilate it, turn it into nothing but vapor, we have to follow a very specific set of rules, the rules of thermodynamics.
So it's a 4-stage journey. First, you've got to heat the ice just to get it to its melting point. Then, you pump in more energy to actually melt it into water. After that, you heat all that water up to boiling. And finally, you pour in one last huge burst of energy to turn it into steam. But here's the thing, these steps are not created equal. One of them is the real energy hog.
Whoa, look at that number. It takes more than 160,000 joules to make that one little ice cube vanish. But here's the real kicker. A massive 75% of all that energy gets used up on just that final step, vaporization. Physically breaking the bonds that hold water molecules together to let them fly free as a gas takes a ridiculous amount of power. And remember, that's just for an ice cube. Imagine doing that to a military target.
And this, right here, is the core problem. You need a colossal amount of energy, and you need to get it to a target instantly, over a long distance with pinpoint accuracy. So physics gives us a few options, and each one has incredible strengths and, as we're about to see, its own show-stopping weakness.
All right, first up is the one we all know and love from the movies, the laser. It's that classic, focused beam of pure light, and it seems like it should just be able to burn a hole through anything it touches. You see, in the perfect vacuum of space, a laser is the ideal weapon. All its energy is perfectly aligned, traveling in a dead straight line, ready to deliver a powerful punch exactly where you aim it. But here on Earth, it runs into a big invisible problem.
That's right. The very air that we breathe is basically in a constant fistfight with a high-energy laser beam. From the second it leaves the weapon, that perfect beam starts to lose its focus and its power, all thanks to a few stubborn laws of physics.
So the beam gets soaked up by water molecules and scattered by dust, which is bad enough. But the biggest, baddest problem of them all is something called thermal blooming, and it's basically a form of self-sabotage. The laser is so powerful, it literally cooks the air that it's traveling through.
What's happening here is that the heated air becomes less dense, and it starts acting like a flawed, blurry lens. It makes the laser beam spread out and lose its focus. And the more powerful your laser is, the more it heats the air, and the worse the blooming gets. It's this vicious cycle that physics just bakes right into the system.
Okay, so if the atmosphere pushes back so hard against lasers, is there another way to get that energy out there? What if, instead of a super-focused short wavelength beam, we used a much longer one? This brings us to microwaves. Microwaves are a totally different animal. They aren't designed to melt armor on the outside. They're all about getting what's called a soft kill. Because their wavelength is so much longer, they can pass right through a target's outer skin and attack its most vulnerable part, the nervous system, the electronics inside. A high-power microwave beam basically turns a target's own internal wiring into an enemy. It creates these massive electrical currents that surge through the circuits and completely fry all the delicate little computer chips and control systems. The drone or missile doesn't explode, it just becomes a useless hunk of metal falling out of the sky. The major downside, though? Rain. Water molecules just love to absorb microwave energy, so a heavy downpour can act like a giant shield. So our final category isn't a wave of energy at all. No, this is a beam made of actual stuff, all of it accelerated to unbelievable speeds. We're talking about particle beams. I want you to imagine a fire hose, but instead of water, it's shooting a torrent of microscopic cannonballs at nearly the speed of light. Instead of just heating the surface, a particle beam punches deep inside a target, dumping its energy all along its path. In theory, it is the ultimate armor-piercing weapon. But, you guessed it, it has its own violent, complicated relationship with the air.
The beam suffers from this really bizarre problem called the hose instability. As the stream of charged particles zips through the air, it generates its own powerful magnetic field. But then, and this is the wild part, that very same magnetic field pushes back on the beam, causing it to wiggle and thrash around uncontrollably, just like a garden hose flailing around when you let it go.
So how in the world do you tame that wild hose? Well, as Philip Nielsen points out in our source material, the potential solution is just as clever as the problem is complex. You don't fire one long continuous beam, you fire it in a series of super short pulses, kind of like a machine gun. Each little pulse is so short that the instability doesn't have time to build up, and you leave just enough of a gap for the air to forget what happened before the next pulse arrives.
So we have lasers that fight the air, microwaves that get stopped by rain, and particle beams that basically thrash themselves apart. After seeing all these huge challenges, where does that actually leave us? This table really sums it all up, doesn't it? Each one of these technologies offers a capability that seems like it's pulled straight from science fiction, instant, precise, and incredibly powerful. And yet, each one is met by an equally powerful counterpunch from the fundamental laws of physics. Beating those laws is what separates a weapon on a drawing board from one on the battlefield. And this really is the great question. The potential to completely change warfare is undeniable, but so are the physical roadblocks. Overcoming them isn't about brute force. It's about a deep, clever understanding of the very fabric of our world. Whether that's even possible is the multi-billion-dollar question that scientists are still working day and night to answer. Thanks for joining us on The Explainer.